long as you don't mess with it or take it, you're all right. Okay.
I'm nervous now.
You're nervous now? Well, then move to the other side. No reason to be nervous. I wouldn't put out anything here that would hurt you. Okay? Unless you really gave me a reason. Anyhow, yeah. Go ahead and let that alone, please. Good man. Thank you. Okay. All right. I think, well, we're getting ready to start. Hello.
Hello. How are you?
Doing well. Do you need a video release?
Sure.
Here we go. Why don't you go ahead and you can take that back, and if anybody else comes in, you can just kind of pass it around. When you get yours filled out, just put it on the bottom of the pile. Okay. Producer Paul, how are we for time? 2 minutes?
2 minutes.
Yes, sir. Okay. Since we're on the web today, okay, we are broadcasting this event live for people who cannot be here. Okay, and because we're doing that, we're going to ask all y'all to be on your best behavior. Okay? Any question you have, you are welcome to raise your hand, and I will take your question. Okay? I will answer any question you have, adults as well as children. And parents, if you want to ask me about how do I teach that, that's a legit question, not just about the science. Happy to answer that. Have you all been able to find the downloads on the web and get them? Everybody got them and found them on the web? If you go to explorescientific.com, and the name of the activities were posted on the Homeschool Hub. You just type in timing the eclipse was one, eclipse flip chart was another, and it'll come up, and it looks like you're shopping, but the cost is $0, and they'll email you a download link, and you can download the PDF and go ahead and use it. Please let go of the power cord, young man. I will not ask again, okay? So if you have trouble with keeping your hands off, just move your seat, okay? Otherwise, let's follow instructions, okay? Thank you. Now, and we are just waiting for the go signal from our producer. We are live? Okay. Welcome, everybody. This is Dr. Daniel Barth. This is a special edition of the How Do You Know program and a special presentation of Explore Scientific. We have with us today parents and kids from the Northwest Arkansas Homeschool Hub. Can y'all give us a hooray? Hooray! That's right. And we're here because I opened my big mouth as usual. And I said, hey, who wants to learn about how to do science, real science with the Eclipse that's fun and easy at home? And I figured I'd get 1 or 2. And then before I knew it, I had lots and lots of responses. And so my good friend Scott Roberts, who runs this company, said, well, you can use our store. And so we're thrilled to have you here. Back is to the sun. And it's easy to do. Now, it turns out that there is something called a pinhole camera, and this used to be a thing back in the day, but you can make one with basically an oatmeal box. You can make one with a piece of cardboard. And I did this just to show people. There's a little hole cut out like a triangle. This one's like a square, and this one's like a circle. And I don't know, the sun is playing games. If the sun comes out strong again, I'll show you this. But this piece of cardboard, when we put it up here, you do not see a triangle, a square, and a circle. Everything you see is round. Why? Because it's not about the shape of the hole. It's about the thing you are projecting an image of. This works like a camera and projects an image of the sun onto the wall, the ground, piece of paper, and you can observe the eclipse that way. And since you're holding it here and looking at the projection that way, your back is to the sun and you are completely safe. Now, you might think, yes, sir, question. Again, louder, please. Oh, if you want to, I have a pair up here. If you want to try them after the program's over, you're welcome to. Okay. Um, and you might say, well, do I have to poke a hole in a cardboard? Mom, should I have one of these? Right? You can hold this up. You can hold this up, and it will project for every hole in the colander. It will project an image of the sun. And during the eclipse, you won't see round dots. You will see the sun as a crescent. You will see it as a crescent of light. Every tree is a pinhole camera. If you're observing the eclipse and you stand in the tree's shadow and you look at the ground, you will see hundreds and hundreds of little, instead of little round dapples of light, you see these beautiful crescents as the eclipse progresses. So anything that projects an image of the sun is a legit way to see an image of the sun. Now, you can use a pair of binoculars to project an image of the sun, and I'm going to show you how to do that safely. I have a tripod here and a pair of binoculars that I borrowed from our friends here at Explore. And if you uncover one side, and I have some blue tape here, so I'm going to go ahead and set my binocular up here, and I'm going to take some blue tape. There are professional binocular adapters, but I'm all about inexpensive. And so you can take your binocular and you can just tape it onto a tripod like this. And if I had a little more bright sun, there we go. Oh, let's see. Let's see. Here we go. Indeed. We'll try again. What you can do now, this is the front side of the binocular. And when it's sunny, I just adjust this so the shadow of the binocular is small. And at that point, I do not, oh, I wonder if the sun is being projected. No, you don't. If you can't put your eye there, your hand isn't safe either. You take a piece of paper, and if you've got it aimed right, what you will get on here is a beautifully focused projection of the sun. And that can not only help you see the eclipse, it can help you document it. Now, a binocular, how big the image is depends on how far away it is. So if you have a piece of paper on a clipboard, what you can do is, oh, I'm starting to see the solar eclipse. And so at the start, your solar eclipse will look like this. And at some point, you will just see a little small nibble, like a bite out of the cookie. When you do that, this here, friends, is called first contact. And you're going to record the time as accurately as you can. And then what you can do with this projection, there's a couple of fun activities you can do. One, you can go ahead and every 10 minutes or so, you can make a sketch. Now, our eclipse, we're going to see first contact about 10:23 in the morning. Now then, 10:23 in the morning, you want to set up and you want to, if you're going to have your binocular, if you got your colander, whatever you have to observe, you want to start looking about 10 minutes early because your exact position on the globe matters. If you're observing it in Springdale or in Bentonville or in Fort Smith or in Elkins or in Little Rock, the time will be different. So you want to start observing plenty early, okay? And when you see that first contact, you go, wait, is it there? And at some point you go, yeah, definitely it's there. And you can go ahead and with a series of images where you've got progressively more of the sun, and forgive me because I'm not drawing real accurately here, and we'll get at maximum to about like this right here, which is about 65% solar coverage from the moon. We are not far enough south to be seeing what we call the path of totality, where the entire eclipse is visible to us. But we'll be able to document this and to record the times. And later, of course, as it moves away, then it starts getting smaller. And I'm drawing it backwards, sorry, because it's moving across this way. It'll start to get smaller and then smaller. And finally, you'll have last contact. And this last contact will occur for us at about 126, between 120 and 130, depending on exactly where you are. So most people are quite amazed that this whole thing goes across more than a couple hours of time. The fascinating thing about this, it's not just seeing the shape of the shadow on the moon that's on the sun that's changing. What you're actually watching is the moon traveling across between us and the sun. The moon is getting away and casting a shadow.
Actually doesn't have much to do with the eclipse thing, but it's still solar. Earth's axis has a wobble that takes 26,000 years.
Earth's axis does have a wobble. It was discovered by Anaximander, who was a Greek astronomer, and he was using records from about 800 years earlier. So yeah, this has been known for almost 2,000 years. And it's fascinating, and you have to have data across. This is the power of science. This was discovered because people were collecting data for many years and recording it and writing it down, and only when they were long dead were people in the future able to use their records to discover this unique motion of the Earth. So let's go ahead here. Eclipse timing, which is our first activity. And basically, just going ahead and recording the exact time, and you can get your GPS location. That data is valuable to scientists. There are websites where you can upload and you can say, here's my solar observation. First contact was here. Last contact was here. Because believe it or not, even today, 2023, after thousands of years of astronomy, we are still refining our understanding of the orbit of the moon and the motion of the Earth. To say that the science is settled, that's the mark of a fool. Excuse me for being blunt, but this is my passion. This is my job. Oh, the science is settled. No, it's not. Science is never settled. You're always allowed, encouraged, and we demand that you question. You do not accept science data from your elders without verifying and testing, because it's the little tiny errors, those are the cracks through which new knowledge emerges. Question. Okay, good question. What does it mean science is never settled? Have you heard of Albert Einstein? And you know there's a sh in Einstein? You know why there's a sh in Einstein? Because Einstein said Einstein. It's the way we say it in Germany. Okay? We always try to be respectful and say people's names the way they say them at home. So you know who Einstein is, right? Famous scientist. Do you know why he was famous? No. He refused to work on it. But that's another story for another day. Why Einstein was famous, he was the first man in 350 years to make any significant correction to the work of Isaac Newton. Have you heard of Isaac Newton? Question. Yes. Is, was, and always has been. This could be a whole nother passionate rant. Here's a question for you. Here's a question for you. Tell me your name. Maddox. If we have a rock on the bottom of the ocean, or a rock on the seashore, or a rock on the mountaintop, are they all rocks? Yes. The people who said Pluto is not a planet said it's not a planet because where it is. I think things are defined by what they are. Right? Concrete is defined because there are things about concrete that we can feel, touch, test, hardness, density, mass, all sorts of things that make it concrete. And we can't take a hunk of concrete and take it to the moon and say, it's not concrete no more because it's not in my parking lot. Pluto is a planet because it has all the planetary characteristics, and it's not about where something is, it's about what something is. This was one of the greatest mistakes in modern history, and this terrible idea will end up on the ash heap of history. My friend Clyde Tombaugh discovered Pluto. It was a planet then. When we sent the New Horizon probe, we found it has features. It's round. It has a world. It has geology. It has oceans of nitrogen and methane. It's a world. It's small. It's far away. But if you had relatives who lived in California or Canada or Madagascar, wouldn't they still be your folks? Of course they would, because of what their relationship is with you, not because of where they live. Pluto is a planet. You can take it to the bank. Good. Do you know you're being happy with the answer doesn't make any difference? It's 90 billion. 97% of science today. Open your backyard. Another question.
Sorry.
Don't apologize for questions. Stop that. Yes, sir? No.
Why do people?
No. Okay. Now, listen. You got 2 ears, 1 mouth. Listen twice as much as you talk. No more apologizing. Thank you. Now, what's your question? Look at the sun. You cannot put that will injure you before you can say ow. Your eye has no pain sensors. You will damage yourself before you know it's happened. And it will be less than a second. You have to observe safely. You have to follow the safety rules because the sun... So, let's talk about if you have a binocular or using a piece of cardboard, you can do this lovely flip book activity. What you're going to do here, index card, you should do is take a quarter, right, or a Gatorade, and each circle. Hold it on your binoculars so you've got your eclipse, and you're like, okay, first one, and you get the next one 5 or 10 minutes later, and you make another one, another one, another one. And since all the circles are in the same place, you can then make a flip book, and you can see the moon passing across the sun. It's lots of fun. It's easy. Kids of every age can do it. Even your parents could pull it off, I'm confident. So it's so easy and so much fun. And that kind of thing, you know, have you all made little flip books with stick figures running and doing stuff like that? Sure you have. This is a chance to do a flip book of the moon passing across the sun. It's a brilliant activity. It's lots of fun for everybody. Now, you might notice, oh, hey, if I'm timing this and I'm drawing that, maybe I can't do all these activities at once. That's true. That's true. You have to make choices about what you're going to be doing. Okay? You have to, I've included 4 activities in this packet, and maybe someone does one, someone does another one. You share results afterwards. Scientists do this all the time. We do different experiments, and then we share data. People say, well, how do you know? How do you know this physical principle actually works? We have what we call that is wins of evidence. Another, and it turns out we get the same answer with different methods. We're much more confident that we're right. And oftentimes when we're doing science, we're actually going ahead and we're doing things out to the very limits of our personal ability and the ability of our equipment. Scientists are often doing things where, well, we think if we do this right, we can possibly detect the explosion of a star in another galaxy. And it's going to be really hard to do, and we're going to have to, but science is all about pushing the boundaries of what can I do, what can my equipment do, and trust me when I tell you, there is no piece of equipment on Earth that is of any value without a skilled hand at the controls. You are the astronomer, okay? This is a binocular. That's a telescope. That's fine. They are of no value without someone who has skill and passion at the eyepiece, because you provide the human side of the equation. You provide the skill, the motivation, the dedication, and recording what you see. If you're just out to look and have a good time, it's like looking at a pretty picture. It's fun. It's interesting. I like that. But when you're recording and sharing with others, then it brings a whole nother level of value to what you do. One more.
It says something interesting. If the human brain were a computer...
We're not talking about the brain today, young man. Let's focus on Eclipse. We're going to focus on Eclipse, okay? Thank you. So, flipbook activity, first contact activity. We've also got some other things in here, and we've talked about observing with binoculars and how to do that. I want to take a minute and erase my board, and I'm going to show you how to make a solar eclipse simulator. So, we can go ahead and set up any way you like to project the sun. You can use a pinhole camera. You can project with a binocular. You can look at a projection under a tree. There are lots of ways to do this, but essentially you have to have some way so that you can get the same size image every time. If we take a look, and I'm going to draw a nice big circle for you. If we take a look and we say, oh, first contact with the sun was at this point. Okay. About 2 hours later, where's the last contact? It's right there. And then when the eclipse is at its maximum, we should get something that goes something like this, and this portion will be dark. Now, if we go ahead and we connect these lines and we draw a perpendicular through here, now we can go ahead and take, again, if we're using a disc, right, you can go ahead and take that disc, and let me have some of my blue tape here. Oops. I'm going to tape my ruler up, and what I'm going to show you is if we put our ruler, this should essentially be a complete circle. And so if we go ahead and we put our ruler so that these two are parallel, we should be able to take the disc and basically move it along there, move it along this ruler, and we'll be able to see a simulation of the path of the moon. Because it's not just a shadow that's changing. It's the path of the moon across the sun. The moon is moving in between us and the sun. That's why we have an eclipse. A lunar eclipse is the other way. The sun is on one side of the earth, the moon is on the other, and the moon travels through the earth's shadow. The moon never goes completely black because the earth bends light around itself. And so the shadow is never completely black. So the moon will look kind of orange to even deep red on a lunar eclipse. And lunar eclipses are more frequent. That was put this way. It's easier to observe a lunar eclipse than a solar one. A solar eclipse is visible in a small band over a small part of the Earth. Lunar eclipse is usually seen by about 2/3 of the surface of the Earth. So it's much easier for more people to see. Question?
Is there a bathroom there?
There is. All the way back and on your left. The nice lady right there will help you find it. Okay? Yes, sir.
Solar eclipses
Happen about twice a year. Does that surprise you? Eclipses about the same. Now, here's the catch. Solar eclipses, although they occur twice a year, what we call the path of totality. If you drew an area on the map, and there's a map inside you can look at, and you can see an area about 50 miles wide, that's hundreds of miles long. If you're standing in that strip, you can see a total eclipse. Outside the strip, you see a partial eclipse. These things happen about twice a year on average, but the Earth is 70% water, so about 2/3 of them or more happen on the ocean, where the only way to see it is if you get a cruise ship and you go there. A lot of times they happen in places in the world where we don't live. Africa, Europe, Antarctica, across the Arctic. And so there are people, and I know some, who are eclipse chasers. They take trips a couple of times a year and they go to remote parts of the Earth to see these because they are so fascinated with them and it becomes a hobby for them. But eclipses happen quite regularly. This year, in the next 12 months, we've got 2 that crisscross the United States. They're both visible in the Midwest. So right now, we are very lucky. And if you go, you can go on the internet, you can go on to Google or other websites, and you can say, eclipses in North America in the 21st century. And there are places where they show you all these and what year they happen. But if you look at total eclipses and annular eclipses, we have about 2 per year. And they tend to happen 6 months apart. And that has to do with the geometry of the Earth, the Sun, and the Moon. And going that far down the rabbit hole requires a bit more math and study. So I'll just leave it there. Okay? Let's talk about how an eclipse happens and what we're actually seeing. Why is this eclipse an annular eclipse and not a total one? Why does it matter? It turns out that if we have the Earth here and the moon goes around, I'm going to exaggerate this. The moon's orbit is actually not round. It's an ellipse. It's an oval. Okay? Ellipse is a mathematical term. Oval is an artistic one, but there you go. When the moon is far away from the Earth, we call this apogee, which is basically Latin, far away from the Earth. You can think A for away. When the moon is closer to the Earth, we call this perigee. And P for pretty close, far away. That's how you remember that. Now, the thing is, when something gets closer to you, it looks bigger. If this is a circle, and I'm seeing you with your hand, and as it moves closer to you, it appears bigger in your field of vision, right? Something comes closer, it looks bigger. You were probably going, scary bald guy. What's your question, sweetie?
If the moon's closer or farther away affect how, like, the course of an astronaut's journey to the moon?
If you were taking a rocket ship there, yes, it would matter because the difference is close to 85,000 kilometers, longer one way than the other. So yes, it would make a difference. Most of the time, the astronauts are more concerned that they get there during the moon's daylight time, because on the moon, the day is 700 hours long. You have 14 days of daylight and then 14 days of darkness. Question.
Would it change weather if the moon was farther away?
It changes tides, but not weather. When the moon is close, tides are higher.
How does that work?
than when the moon is far away. So, yes, it does affect us directly, but not in terms of cloud, sun, storm, rain. No. But tides, yes. And if you're having like a hurricane where you're expecting a flood and it's at perigee, then your flood's going to be worse because the moon will raise the tide and the storm raises it some more and it can make it more devastating. So, yes, that can be an effect. Yes, sir.
When it's farther away, does it affect the weather on the moon?
No, there's no real weather on the moon except daylight and darkness because there's no air there. And Galileo figured that out in 1609 because when he watched the moon moving through the sky, sometimes the moon will go across in front of a star. And what Galileo noticed is when the moon went across in front of a star, the star went out like that. And what he noticed looking outside at his home, that when our star, the sun goes down on Earth, it gets dimmer and redder. And none of that happened on the moon because there's no air there to change the way we see it. So Galileo realized in 1609. The other thing he realized is that he saw things he thought were seas. He was kind of right. They were old seas of lava that had hardened billions of years ago. The dark parts on the earth are called maria, which is Latin for seas. Mare humorum, the sea of moisture. Mare procellarum, the sea of storms, right? Mare fecunditatis, the sea of fertility. Mare tranquillitatis, the sea of tranquility, where we first landed in 1969. So he said, there's seas, and they published it, and people said, wow, seas. And we've kept the name for 400 years, even though about less than 10 years later, he figured out they weren't real seas because there was never any clouds, never any storms, never any fog. He said, if there's no weather, there can't be water. And then he noticed that stars went out instantly. He said, no air, no water, no weather. Okay? And that's how we know. Now, here's the thing. When the moon is at apogee, far away, the moon appears smaller, and again, I'm exaggerating. It's about a 10% difference between these two. Am I losing papers? That's okay. Let's not litter, shall we? There we go. Now, the thing is, although this is just a 10% difference, the size of the sun is between these two. When we have an eclipse at apogee, the sun is here and the moon is not quite big enough to cover it. When we have an eclipse at perigee, the moon is actually appears, because it's closer, to be bigger than the sun's disk, and so it blocks it out entirely. Question, young lady. What's that now? Oh, how dark? If you're in one of these, a total eclipse, which we're going to have next April, and you're in where you can see it go totally dark, it becomes dark like nighttime. Birds stop singing and go to sleep. The stars come out in the sky, and it is completely dark, and it lasts only a few magical minutes. It never lasts more than about 3 or 4 minutes, and then the edge of the sun comes out again, because the size of the moon, when it's at perigee, is so close to the size of the sun. Yes, ma'am?
Why does eclipse blind you?
Actually, it isn't the eclipse that's dangerous. It's the sun itself. The sun gives you ultraviolet, which can make you more tan, right, if it touches your skin. But that same ultraviolet, your eyes have no protection against it. So if you're looking at the sun, and most people don't because it's too bright, but if you're looking at the sun, that ultraviolet light can hurt your eyes. The problem during an eclipse, when most of the sun is covered, you're like, oh, that's not so bright, but it's much too bright for your eye to see safely. So we can never look directly at the sun. We want to use projection, like with shining through a pinhole or projecting through a binocular. Or if you're using a telescope, you have to have a correct solar filter. And we have those. Those are available. They have them in the store. But you don't ever want to try to look at the sun without proper protection. Anybody else have a fun question? Okay, so what's happening here? On our Earth, let's say this is the moon and the sun is up here. What's happening is the moon's shadow, which is actually shaped like a cone, is projected down onto the Earth. And down on the Earth, this is never more than about 50 miles wide. And as the Earth turns and the moon moves, what happens is this projects a curve, what we call the path of totality. If you're standing along that exact precise 50-mile wide path on the right day in the right place during an eclipse, you will see totality. If you're on either side, you don't see a total eclipse. You see a partial eclipse. How much you see depends on how close you are to the path. This eclipse is going through South Texas, and it never gets closer than about a couple hundred miles to Arkansas this time, several hundred miles away, actually. And so we're going to see about 65%. My brother, who's up in Wisconsin, he'll see about 35%. If you were down in Texarkana or in North Texas, you'd see 70, 80, 90% as you got closer, but only in that one little strip of land at the right time, on the right day, will you see totality. So it's a very special event.
Do we know if the moon or sun is bigger?
If the moon is?
Do we know if which one is bigger?
Oh, the moon is much smaller. It would take, if you looked at the sun, the sun is about 400 times wider than the moon, but it's also 400 times farther away. This is a coincidence. As the moon orbits, the Earth is constantly speeding it up, those tides we talked about. The moon pulls on the tides also pull on the moon. The moon is speeding up, the tides are speeding it up. So the moon is slowly spiraling farther and farther away. At some point, hundreds of years from now, maybe thousands of years from now, we'll no longer see total eclipses at all. It won't be possible from the Earth because the moon will be so far away, the shadow won't reach us anymore. Right now, we are in this wonderful era. We happen to be born right and living right. We're in this era where we can see both an annular eclipse where the moon is far away and doesn't quite cover, and a total eclipse where the moon does cover the entire sun. And that total eclipse, that's what happens next April. Okay, and that one is going to come right through Arkansas. And so we hope that you all get a chance to see totality at that time. Question?
Will it be in this part of Arkansas?
I think totality is going to be a bit south of us, but I know Little Rock's in the path and areas north of Little Rock, and it kind of goes from the southwest corner to the northeast corner. We're in the northwest corner, so we have to move more towards the center or south of the state to see it all. Yes, ma'am?
Will you be taking that trip there?
I don't know. I know folks here from the store are going down. There's a town in Texas where both eclipse lines cross, and some folks are going there for the 14th, and they'll be back again in April. I'm not doing that journey. I have invitations from some people to go down to the Little Rock area, but we'll see. Yes, ma'am.
April coming up?
Coming April, yes. I think it's April 8th, I think. But, you know, check me on that. But, yes. And we'll have more programs and things like that. Now, we've kind of shown you a lot of fun activities and way to observe the sun safely. So how many of y'all are excited about seeing the eclipse on the 14th? Yes, I'm glad you all are doing that. Parents, did y'all figure out some fun stuff you can do with your kids today? Okay. If you have not, I hope that you will go ahead and if you haven't already, please go to our Explore website and download these eclipse activities. The other thing I'm going to give to you today When I was up at the U of A for 9 years, what I did is I trained teachers, mostly K through 8, to teach astronomy to children. And my book is called Astronomy for Educators. It's now the most popular astronomy lab manual in the world. More than 10,000 schools in more than 60 countries. And my book is free to you. When I wrote it, I gave it to the U of A and I said, give it to everybody. And they're like, but why? Do you know how many people helped me become the man I am and the scientist I am? So many. So many. People that did stuff that was worth emulating and people who did stuff badly. And I said, I'm not going to be like you. My daddy wasn't an educated man. He was really smart. He said, every person on God's earth is here to teach you something. Most of them are here to teach you what not to do. You've just got to pay attention. But I owe a debt to people who did for me what I'm doing for you today. When I was 10, my parish priest, his son was my best pal, and he had a telescope in his office that I thought, and I bugged him relentlessly, oh, Father, can we take your telescope out? Can we, huh? Please, can we? I was annoying. Somebody should have spotted me as a future scientist. Finally, he called all the parents in the parish and said, it's going to be nice. Come on over. Most of the kids stayed for about a half hour. Father and I were there for a couple hours. And I'm like, what's the yellow one? He says, you know how to move the telescope? Point it and see. It was Saturn. There were rings. There were tears in my eyes. It's like I'm seeing the light that fell on that planet 6 hours ago, and I'm seeing it now the way it was then. Because when we look out in space, we look back in time. That night changed my life entire. It changed the whole course of my life because someone said, yes, come on out. Look through the telescope. See God's wonders. They're there for you. You just have to look and pay attention. Everything in the heavens is a miracle, y'all. Most people don't bother to look up and appreciate them. That man, God, I love him. He's gone now. And I had a chance when he was 93 to see him again and tell him how much that night meant to me. And I'm hoping this day and this eclipse will be that spark for you. Oh, I want to set the hook hard like you're a trout in my stream. I want to reel you in. I want to make you a lifelong observer and scientist and astronomer. Because you can't just do it when you're old. You can do it forever. There are so many things we do when we're young that we can no longer do as we age. Admiring and observing and documenting all the glories in the heavens are one of the things we can do from when we're very young until literally the day we die. If I pass one night out in my backyard at the telescope, I will not be unhappy because I will have died doing what I loved for my entire life. I have so much passion for this. I sometimes scare people. No, really, I've had students go, oh, Dr. Barth is interesting and stuff, but dang, he's scary. He gets up and he yells and he stands on the desk and he waves his arms and I'm afraid he's going to have a stroke. He gets so, I'm just like that. Ask my kids. So all I'm going to tell y'all is I would like you to go home and download that. If you have a telescope or if you're thinking about one and you say, well, it would be hard to learn to use a telescope. I wrote another book for you. This one's on Amazon, and yes, I'm gonna say this is for sale. And yeah, I make about $0.25 if you buy one. So I'm not gonna get rich by telling you about this, but I hope I'll make your life rich. What I did is I went through here and I wrote this during COVID because during COVID, telescope sales boomed. People wanted something they could do in their backyard by themselves. And then they said, but how do I learn all this stuff? How do I learn to use the telescope, point it, read a star map? How do I know how to find the constellations? How do I know what I'm looking at? So I took 44 years of teaching astronomy and I put it into this book, Star Mentor. And with this book in your hand, it's like having an astronomy instructor right by your side. And it's not like you have to start on page 1 and go the whole, and there's lots of pictures, y'all. I drew them all. So if they're lousy pictures, I don't want to hear about it. It's as good as I could do. But
Can I see one?
yes, you may.
Thank you.
But I wrote that for people who said, I want to get into this. I'm afraid it's too hard. I don't know if I can learn it. And my answer, whenever somebody in my family, and there are 12 kids in my family, there's 7 brothers and 5 sisters, I was always fighting somebody. And although I was third from the bottom, I was always the littlest one. Danny can't do that. My answer to that from the time I can't remember and was young. Anybody else want to poke through? Yay, go ahead. Circle around.
I think you just made
My
one
answer
point.
was just hush and watch me. I was ruder than that, but we'll just leave it there.
Oh my god.
Hush and watch me. Yes, I can. Determination will take you farther than raw talent ever will. Your desire, your passion, your enthusiasm. Raw talent is no substitute. I know lots of talented failures. I know very talented bums. I know very talented people who can't support themselves. But every passionate person I know is a success. You don't have to be brilliant. You just have to keep at it. I am not a brilliant man. I'm a passionate man. And I've been learning about astronomy for more than half a century. If I seem like I'm smart, it's not because I'm brilliant. It's that I kept at it. You can too. And that's why I wrote the book Star Mentor, because people needed someone standing next to them to help them. And I couldn't be there for everybody. But I could put it down on paper. And I kind of boiled down. I sat down and I thought, well, and I looked through all the courses that I've taught, middle school, high school, university level. And I said, how do I help people learn this when I'm not there for them or when I'm no longer here? And so that's what I did that for. And I hope all y'all will get Astronomy for Educators, because it's a lot of hands-on model making fun stuff you can do at home, even on a cloudy day. And all of it is conceptual. Parents, you know what I'm talking about, right? I have kept I've kept basically all the math out of it. Now, each activity, and there's like 3 dozen in that book, each activity has additional, you want to go farther with the math, it has additional stuff to do to go farther, to go deeper, to learn more. But all of it is accessible even to the younger children in the audience today. Okay? You can absolutely have someone with some markers and some ping pong balls and some bottle caps, and you can make a model of the Earth and Moon, and you can understand how the phases of the Moon work and how the orbit of the Moon works, and you can understand all of this on a tabletop for about $1, 2 50-cent ping pong balls and some markers and a couple of bottle caps off a milk jug. You can make a whole model of the solar system. That's in that book. Because I wanted to have teachers, even if they were at schools that didn't have money, that were out in the country, they didn't have resources, they'd never taught astronomy before. I wanted to make it accessible for those teachers to share with children like y'all. That's what that book's for. So I'm hoping everybody will download a copy. You can put it in Astronomy for Educators in any search engine, it'll come up. The website is called ScholarWorks. It's run by the U of A. It's the U of A Library Press who puts it out. So I hope you'll all get a copy of that and look through it, because there's going to be some stuff you're going to, ooh, this looks fun. Well, this can't be science. It looks like fun. We're playing with clay. We're working with models. Yes, it's real science. Yes, it's real science. The point is, got to set the hook. Got to set the hook. Have y'all had fun today?
Yeah!
So, and this is for my friend Scott Roberts. Would you all like to come back in November and do it again for the moon observations?
Yeah!
Okay. Parents, if you go to our website and you leave a comment, if you go to the NWA Homeschool Hub, you leave a comment. And I'm thinking about November 17th, and we'll do an activity set like this on how to observe and do science with the moon. Okay.
Speaker on the sales guy, 15% off everything in the store.
And like I said, I browbeat my friend Scott Roberts. The Eclipse glasses are normally like $250, and I said, no, give it to him for $1. So if you want some, they're not going to be that price tomorrow. He's only for people who come, because he's a businessman. He's all about the nickel. Where's the next nickel coming from? But basically, y'all getting them at cost today if you want them. And I got him to do that because I said, I'm going to set the hook. They're going to be passionate about this. They're going to be excited. So, no, it's not online, and it's not for anybody who's not here today. It's y'all's prize for showing up. So if you have questions, we're going to wrap up the program now. And if parents have questions about teaching this, or if your kids have questions, I'll be glad to hang out for a while, answer y'all's questions. But for right now, we're going to wrap up this broadcast. And thank you all for being part of this program today. We appreciate you. Okay.